Hello everyone. Here in this lecture, I want to show you the method of derivation of Euler's equation of motion along a streamline. In this channel, already I have posted one video about the derivation of Euler's equation along a streamline. Here in this video, I am going to add a few more points. Okay, so and I'll provide the link of the previous video also in the description box of this video. Okay, so if you want to watch that one, you go to the description box of this video and then you will get the previous one. Okay, so here we are talking about Euler's equation of motion along a streamline. Yes, Euler's equation of motion can be derived also in Cartesian coordinate system using x, y and z coordinates. There you will get total of 3 equations. Along x coordinate one equation, along y coordinate another equation, and the third one you will get along z direction or z axis. And these are called x momentum equation, y momentum equation and z momentum equation along x, y and z axis or along x, y and z directions. Okay, so first is streamline. You know the definition of streamline. Streamline is nothing but an imaginary line tangent to which at any point represents the direction of the instantaneous velocity vector. Yes, of course it is instantaneous. The direction of the velocity vector may change from time to time. At different times, the directions may be different at a fixed point. Okay, if the flow is unsteady. But if the flow is steady, then for a particular location or for a particular point, the direction of the velocity vector won't change with time for steady flow, but for unsteady, it may change. So according to the definition of steady and unsteady flow, this can be easily said. Okay. So here to derive Euler's equation of motion, one assumption. First assumption is the flow is along a streamline, and the next 2 assumptions are there. Next assumption is what? It is applicable only for inviscid flow. That means non-viscous flow. That means effect of viscosity will not be considered. Okay. The fluid or the flow will be considered as inviscid or non-viscous flow, and this can be assumed in case of high speed flows where the flow velocity is very high. In those cases the flow can be considered as inviscid flow, because in that case force due to viscosity, okay, forces due to viscosity are very small as compared to the inertia forces. Okay, if inertia forces means if velocity is high, then inertia forces will be very high. Okay, and if inertia forces are very greater than the viscous forces, in those cases effect of viscosity can be neglected at ease. There will be no error at all. Okay. So whenever you are not considering the effect of viscosity, the resulting equation is called Euler's equation of motion. Of course, this is the momentum equation. So here Newton's second law of motion will be used to derive the required equation. Okay, that is the first thing. Second thing is, you know that how mathematically Newton's second law of motion is expressed. It is equal to rate of change of momentum, means time rate of change of momentum. say F is the force, M is the mass, V is the velocity, then in that case we can write F is equal to d dt of mv. Okay, here F is force, small t this is time, small m this is mass of fluid, v is the velocity of fluid. So this is the general form of Newton's second law of motion. And one more thing we know, that is F is equal to mass into acceleration. Mass into acceleration, A is acceleration. Question is, both the forms are same or not? Answer is, both the forms are not same. There is a difference. This can be written as this only if M is a constant quantity. If mass remains constant, then this can be written as this. Say, I am going to write this one here. Okay. So the next line next to this is what? Say M is a variable. So in that case, you can write that thing as V dm dt plus M dv dt. Alright? We should write this way. This is product of M and V. So derivative of product of M and V can be written this way. Now if M is a constant, means M does not change with time. Okay, here independent variable is time, t. So if M remains constant, in that case dm dt will become what? It will become 0. So V multiplied by 0 is equal to 0. So remaining thing is only M dv dt. So we write this way, V into 0 plus M, and dv dt is what? This is rate of change of velocity with respect to time, that is acceleration. So this is ma. Therefore this is equal to ma. So what we have got? We have got F is equal to ma, means this form. So this form can be used only if mass remains constant. But if mass changes with time or with anything, in that case, not with anything, only with time. Okay, because here dm dt appears, no other variable is there, no spatial coordinates is there here. Okay, so if with time mass does not change, then we can easily write F is equal to ma. But if mass changes, then we need to write this way or directly this way, d dt of mv, that way. Okay, so first thing was this one. And second is to derive Euler's equation of motion along a streamline. What you need to do? This is the streamline. Okay, S represents streamline. You need to take one cylindrical fluid element. This is cylindrical fluid element. This face, this is actually circular. Okay. This is the length of the cylinder. Along this is the length. Along the streamline, we have taken the length of the cylinder. And this is the axis. Streamline in between this, within the cylinder, it is a straight line because this length is very small, infinitesimally small. Okay, so in that case, this curved line can be considered as a straight one. And what is the length along this? Along this, the length is delta S. And area is how much? Area is delta A. Okay. So, and here we will consider pressure P. Here we will consider another pressure because there is a difference delta S. Say here the pressure is P, then here the pressure will be P plus del P del S into delta S. Like this. Okay. Then we have to do what? Force balance. What I want to say here in this lecture, I am not going to show you the derivation because already I have posted such one video about the derivation. Okay, I provide that link here in the description box of this video. Okay, so we need to consider this force due to this much pressure. This pressure multiplied by this area delta A will give you one force. Another force will be obtained from P into this area delta A, and one more force is there, that is weight of the fluid element. from the center of gravity of this fluid element, weight of the fluid element will be acting in the vertically downward direction. So these three forces we need to consider. And you can say that there are forces on the curved surface of the cylinder. Should we need to consider that force? Yes, effect of that force is there, but pressure is acting perpendicular to the curved surface, and this surface is perpendicular. This surface is parallel to the axis of the cylinder. That means direction of this force and this axis are perpendicular to each other. And we are going to derive the equation along the axis. Okay, along the axis of the cylinder. Therefore, this direction and this direction or this direction, they are perpendicular to each other. So there will be no effect of these forces in the direction of the motion, what we are considering here. Okay. So you need not to consider these forces. You need to consider only these forces along the direction of the flow. Okay. And here this weight and this line are not perpendicular to each other. Yes, in any special case they may be perpendicular to each other. Okay. Say the fluid element is horizontal. Now this is inclined this way. If it is horizontal, in that case weight and the fluid element are perpendicular to each other. Therefore, in that case, there will be no effect of weight in the direction of the flow. But in general, effect of weight is there. So we have taken here general case. Therefore, we need to consider this force also. One more thing, here this fluid element is very small in size. Therefore, we can assume that density within the fluid element remains same. Okay, we are not talking about constant density flow. Here in this case, density may change, but since the fluid element which has been taken is very small in size, therefore we can consider that there is average density rho. Means within the fluid element, density remains constant. Okay. Therefore, what is the mass of the fluid element? That is, mass is how much? Volume multiplied by the density. And weight is how much? Mass multiplied by acceleration due to gravity, that is small g. Therefore, mass of this fluid element is rho into delta A into delta S. Delta A into delta S is the volume, rho is the density, so this becomes mass and multiplied by g. So this will give you the weight. Here how much is the force? This pressure multiplied by the area delta A. Therefore, what is the resultant force in this direction? In this direction. This direction is parallel to the axis of the cylinder. So net force along that direction is equal to how much? This P multiplied by delta A. Okay. Minus effect of this force. So P plus del P del S into delta S into delta A. Then component of this will be along this direction. So this quantity, this weight multiplied by this, say this angle is theta. Then here with a negative sign you need to write that thing, rho delta A delta S G cos theta. Okay, and the remaining thing is same as the previous video, as my previous video. Okay. Now, so this is the right hand side. Later you will get cos theta is equal to how much? Cos theta is equal to, you will get dz ds, where z is the vertical direction. Okay, z is the, later you will get that thing. And f, here we need not to write f is equal to ddt of mv, because here in this derivation we have taken control mass system, and in case of control mass system, mass of the fluid element remains constant. Therefore, this F can be replaced by directly mass into acceleration. So this F means the left hand side can be replaced by rho delta A, this is A, okay, into delta S mass into acceleration. Say acceleration is denoted by AS. S is the suffix, S for streamline, AS. So this way you can write, okay. So you need not to write here F is equal to ddt of mv. Directly you should write here mass is not changing with time because we have chosen control mass system approach. Okay, control volume system approach is there, again control mass system approach is there. If you take control volume system approach, in that case you need to write F is equal to ddt of mv. But if you choose control mass system for the derivation, you need to write F is equal to mass into acceleration. Anyway, whatever be your approach, whether it is control mass system approach or control volume system approach, the resulting equation will be same. So in my previous video, I have taken control mass system approach. Later I'll make one more video about the same topic but using control volume system. Okay. Within the next few days, I'll make that video and post in this channel. Okay. So, so this is the end of this video. If you like my videos, please subscribe to my channel. Okay. Thank you. Thank you for watching this video.